I would like to start by introducing the place I came from, the city of Nizhniy Novgorod. It's not far from here, 500 kilometers to the east from us. And most of you are familiar with Nizhniy Novgorod, even though those who have never been there. I'm absolutely sure most of you, at least once in your life, did the Bogolyubov transformation. Nikolai Bogolyubov was born in Nizhniy Novgorod in 1908. Scientifically, in connection to the topic of the talk, Nizhniy Novgorod is the place where presently most precise clocks in the world are produced. This technology is not based on the ultra-cold atoms yet, but ultra-cold atoms is the next step for this technology. More precise clocks are made only in the labs, but industrially, about 80% of the world production of the most precise clocks, hydrogen masers, are produced by two competing companies located in Nizhniy Novgorod. The world production of those precise clocks about 200 units, and they are used in as time standards in astronomy and for transferring large volumes of data for synchronization of the nodes. And also in Nizhniy Novgorod we run a school for young scientists. It's experimentally based school. You come and do experiments. The amount of people we accommodate is much smaller than here, from 1 to 3 people at a time, but the time students spend there is quite long. It's usually from 1 to 3 months, and it is arranged on in informal way. So if anybody interested, contact me. We cover accommodation and travel expenses. And theoreticians are welcome, because in physics it's about phenomena you can observe, and in most of the physical phenomena it's interplay of different theoretical models. It's the way to feel a connection even between different fields of physics, and at least between different models. You can even think of a very simple example. Suppose you come to our lab in Nizhniy Novgorod and do a very simple experiment. You take a photodiode and shine a laser beam on a photodiode. The photodiode is producing electromotive force, and you connect photodiode to the ground via a resistor. And on the scope, you connect the scope to the resistor and measure the voltage. And on the scope, you would see a trace, voltage versus time. Suppose you have perfectly stable laser, but your signal would be noisy. Where this noise comes from, a layperson would say your equipment is faulty. But we are physicists, we know noise is intrinsic to the nature, and it has its own interest in physics. And at least there are two phenomena contributing to here. Very different phenomena. One is the Nyquist noise, because this resistor is at some finite temperature. And the other is the quantum shot noise, because the laser beam consists of photons, which arrive in which are quantized. So experiment is this is what helps you to understand which phenomena contribute. Now I'm coming closer to the topic ultra-cold matter, and before continuing yesterday's topic, I would like to say a few words about. Yes, please.
So I think you mentioned this yesterday about gas. So why is inside this cavity still gas?
Yeah, so would you like to comment why it is white?
Yes, I don't know. I still don't understand.
Well, it's in reality, this gas here, thank you very much for remembering this point. In reality, this ultra-cold gas is red. And if you look by your eye, just by naked eye, the gas here is red. But this is a photograph on a telephone, on a digital camera. And the intensity, the amount of light coming from this cloud of atoms, it is so high that it saturates the red sensors, and it even penetrates into the green sensor and blue sensor. So this is the artifact from the equipment. Too strong exposure. But if you look with less equipment, just by your eye, it would be red. Thank you very much for remembering my question. Okay, so this is the plan. We shall keep talking about cooling and trapping atoms. We shall talk about atom-atom interactions, and we shall talk about collective phenomena in bosons and fermions. And of course about misconception and challenges. Before continuing with the main plan, I would like to say a few words about practicality of ultra-cold atoms. And first practicality, I will mention two practicalities. First, highly recognized, the other not recognized yet. First, technologically, ultra-cold atoms today are most important for precision timekeeping. Most precise clocks, which are built in laboratories, are based on ultra-cold atoms. Industrially, such clocks are not built industrially yet, but in the laboratories, best clocks are based on ultra-cold atoms. How it works? Let's consider, and second, today is defined via transition between two ground states of cesium. Let's consider just two ground states of cesium. So the valence electron is on the lowest orbit, but due to coupling between nuclear spin and electron spin, this lowest orbit is split into energy levels separated 9 gigahertz apart. So what a clock is? A clock, it's some generator, say based on quartz. And such generator constantly, to stay precise, such generator should compare its frequency omega to this transition of the cesium atoms. These two states, they correspond to different orientation of the nuclear spin and the electron spin. In one state, those two spins are parallel. In the other state, they are orthogonal. So how to compare clock to this clock frequency to the atom? You should, well, technically, inside the cavity, magnetic field, oscillating magnetic field is created at this frequency of the clock. Magnetic field interacts with the magnetic moment of the atoms. It makes electron spin and nuclear spin flip from the parallel to the opposite position and vice versa. So for such comparison, the atom is sent through the cavity, interacts, and then flies back. So the magnetic field interacts with the atom twice, and the state of the atom is measured, and this is how the comparison is performed. And for this purpose, of course, ultra-cold atoms are the best, because the bigger number of atoms you have, the more precise your clock is. And second, when you send your cloud of atoms up and down, this cloud should not spread out. It should not fly away. So the atoms just should have a small velocity spread. And this is what such ultra-cold atoms are good for. And this is photograph of such a device. This is the region where the cloud of atoms is thrown up and then falls down. This is so-called atomic fountain. That's how today's definition of second works, and now even more precise clocks are built. You may notice over there on the window there is a very interesting poster about clocks from Lebedev Physics Institute. Oh, and this is in the second row. This is Nikita who presented this poster. So even more precise clocks are based on lasers which are stabilized using Fabry-Perot cavities, and then frequency of such lasers is again it is compared to now to optical transition in atom. And those clocks are even more precise, and maybe in the future second will be redefined in terms of optical frequency of ultra-cold strontium or ytterbium atoms. So this is one practicality. The other practicality, not as widely recognized as the clocks. There is well, clocks, precision clocks, for example, are needed for navigation devices, for GLONASS or for GPS to work, to synchronize the clocks of the satellites of the navigation systems. But there is another approach to navigation. It's it's your own navigation, not connected to satellites. For this sort of navigation, you need to, if you want to navigate with your own devices, you would need to trace your path. You would need to know where you make turns, and for this purpose, gyroscope is needed. And the best, in principle, the best gyroscope is a Bose-Einstein condensate. So this is schematically I draw Bose-Einstein condensate in the trap, because Bose-Einstein condensate is superfluid. Superfluid does not rotate. It's the world rotates around this gyroscope, but the superfluid stays in place. The problem of such a gyroscope is that well, you need to see your rotation relative to this ring of a superfluid, and all particles inside this ring look the same. That's the trick. And how to resolve this trick? Well, you need to put some marks on the Bose-Einstein condensate, but without killing condensate, because if you touch it becomes hot. And the way to put marks is again lasers. You saw yesterday that focus of a laser beam can attract atoms inside, but also a laser can repel. It depends on detuning. Yesterday, for optical dipole trap, for trapping inside the laser, you considered laser frequency, which is much less than the frequency of optical transition in atom. If instead you make laser frequency higher than the frequency of transition, then such laser would repel atoms from the region illuminated by the light. So Bose-Einstein condensates are fundamentally the devices to build the most precise gyroscope. And this direction is quite undeveloped today. So this is one of the directions you can contribute in ultra-cold atoms. Few points to remind from yesterday. First, you can use on-resonant laser light or near-resonant laser light to pre-cool atoms from a room temperature or from even high temperature to a few hundred microkelvin. And the idea is to turn the laser frequency just slightly, a little bit below atomic transition. Then, due to Doppler effect, an atom moving opposite to the laser beam comes in resonance and feels the light pressure. Then you eliminate some region from 6 directions and get cooling in this region. And to create a trap, some trapping point should be specified in place. And in space, you specify the trapping point by setting magnetic field to 0 and growing away from this point of trapping. That's a way to make trap. So that's a way to make magneto-optical trap. But the temperatures in such trap is still quite high and no degeneracy. And reaching degeneracy can be reached by evaporation. Now you reload, the atoms can be reloaded from magneto-optical trap into conservative trap, which can be in the focus of the laser beam. It's a very nice trap, but in approximately 1 hour or 1 hour and a half, I will talk about problems of this trap, and maybe it will be replaced by an even better trap in the future. So atoms can be trapped in the focus of a laser beam. It's conservative trap. They collide with each other, thermalized. The hottest atoms are lost, and then the remaining atoms thermalize to lower temperature, and this is how they cool. And it's possible to cool down to degeneracy, to occupation of the phase space 1. And for bosons, even bigger occupation of the phase space. So that's trapping observation. Well, as people involved in quantum mechanics, you know, observation, it's a huge field in quantum mechanics. It's not enough to know something about the system. There is the whole science how to see some property of the system. And atoms here, they are quite easy. They can be just seen directly. This is supposed cloud of atoms. You just shine on a resonance laser light. The atoms make a shadow in this laser light. And this shadow is imaged on a charged couple device on the CCD camera. And this could be the photograph of the atoms. From this, you can, from this one can reconstruct the density of the atoms. And all measurements are based on variations of this technique, or most of the measurements, absolute majority. The bad thing about such imaging, the cost of this imaging is that each atom is absorbing a photon, and the momentum, a photon carries momentum, and if you calculate this momentum in terms of energy of the atom, this would be at least fractions of a microkelvin energy. And if you compare to a few nanokelvin energy of an atom, you can see that a photon imposes lots of energy, and the state of the cloud is killed by imaging. So this is destructive measurement. Interactions. The gases are very dilute. A typical distance is on the order of a micron. And there was a very nice question why the atoms cannot come closer. Yes, the lady in the second row asked this question. I hope I will arrive to this question soon. They can easily come closer, but then the three-body process starts, which heats the cloud. And we shall look into such three-body processes today again. The S-wave collisions are dominated because of the large centrifugal potential for high partial waves, and the amplitude for collisions, it can be expressed just via scattering length and the momentum. And for infinite scattering length, the cross section is determined by the momentum of the atom, meaning that cross section is determined by the size of the de Broglie wavelength. And scattering length can be tuned by the interference of two scattering channels. So free state, designated by this dashed line, is brought into resonance with the bound state, designated by another dashed line. And this way, by applying magnetic field, scattering length can be tuned to any value. Okay, the point we stopped at last time. Mean field analysis of strong attraction. Here is the question. This is the naive presentation of the mean field. It's proportional to the scattering length. What happens if the scattering length is large and negative? Of course, let's don't believe into the infinitely negative attractive mean field inside the cloud. We replace the infinite scattering length here by the effective scattering length, which should be on the order of 1 over the Fermi energy. So the interaction is on the order of the effective scattering length is on the order of the inverse Fermi momentum. As a result, the interaction energy is on the order of the Fermi energy, just with a negative sign because this is attraction. And let's see who wins. It's like, remember the problem about collapse of a neutron star. On one side, gravity is pushing inside. On the other side, Fermi pressure is fighting against the gravity. Here, this is Fermi energy fighting against attractive interaction, which is the same order of as the Fermi energy. Well, an experiment has been done, and a gas with such a maximally strong attraction has been created. It's back 2003. See, we are progressing. Yesterday we analyzed experiment from 1995. Today, this is already this century. By the end of the lecture, we shall even arrive to a little bit of future. And actually, John Thomas and his colleagues created such a gas. This is the observation. This is the gas in the trap. Then the trap was switched off, and the gas is expanding. The gas is expanding means that attractive energy is not stronger than the Fermi energy. There was some positive energy inside the gas. So this means that from simple analysis, on the previous slide, we found that interaction energy is on the order of the Fermi energy, and the experiment gives this proportionality value, beta. And actually, since there was, I was told by theoreticians that it was quite not easy task calculating this beta, because this is a non-perturbative problem without a small parameter. There is no small quantity in this calculation, and similar methods were used as used for neutron matter. So this is a connection between nuclear physics and atomic physics. The second question was posted: superfluidity at maximally negative A. Well, there was as you can notice, Bogolyubov, this is the Hamiltonian which appears in Bardeen-Cooper-Schrieffer theory, and the Bogolyubov's version of this theory does not have anything about the lattice. So in the gas, superfluidity of fermions is also possible, and this is the critical temperature. And actually, indeed, the first experiment on creating such a strongly interacting, strongly attractive Fermi gas has shown signatures of superfluidity. Even there was some quantitative agreement with superfluidity. Again, a very simple but very important experiment. Expansion of a gas. Trap is turned off, the gas expands. again, please notice similar situation as with the Bose condensate. The expansion, this was initially a cigar-shaped stretched cloud. It does not expand into a sphere. It expands again into a disk. Here the transverse direction has grown a lot. So this shows that quantitatively the expansion agrees with the equations of superfluid hydrodynamics without rotations. But remember the criticism about expansion of Bose-Einstein condensate from yesterday, that normal gases can expand a similar way to superfluid gases. And those equations of superfluid motions, they're absolutely identical to frictionless motion of a normal gas with lots of collisions. So this experiment, as the authors of this experiment pointed out in the initial publication, can be explained both as a superfluid or just a gas with lots of collisions. See, this on one hand, this is a very dilute gas with about 1 micron, with particles about a micron apart. On the other hand, they interact very frequently. And the solid proof of superfluidity came 2 years later. Property of a superfluid is that rotation does not penetrate into a superfluid. So the places which rotate inside the superfluid, this is empty space. Empty space rotates in superfluid. So if such a cloud was spinned by again dragging it with 2 laser beams at the edges. These 2 green laser beams, they were touching the edges and they were spinned around. So as the gas spinned, it developed vortices inside. And moreover, those vortices, they, if you look at those photographs of the vortices, the vortices form a triangular Abrikosov lattice, which is a signature for superfluid.
May I ask you something? Mm-hmm. So you can expect vortices also for non-superfluid liquids, right?
Yes, exactly.
But why do you think that the presence of vortices is the evidence of superfluidity?
The fact that they build into the lattice.
Only this fact?
Yes. Vortex by itself, yes, absolutely. I fully agree. It's a hurricane is a vortex. It is a vortex. So the gas is found to be a superfluid, and indeed the temperature of the superfluidity was found, the critical temperature, approximately 10% of the Fermi energy. So among other materials, in terms of Fermi energy, it's the highest temperature superfluid. Of course, in Kelvin, that's a ridiculously small value. And its scale, by changing density, of course, you can change the Fermi energy. Fermi energy, it's h bar squared over 2 masses times numerical density enters here. And of course, the gas can be more dilute, less dilute by compressing or expanding the gas, and the temperature appears to be the same. So it's truly in units of the Fermi energy and in no other units. In comparison, in cup-rate superconductors, it's the critical temperature is not 10, but 1% of the Fermi energy. Okay, here, about superfluidity, it was the gas which was pre-mixed There were in the gas there were fermions in two spin states mixed together, and they perfectly form a superfluid. Let's look at significantly different initial conditions. It's one of my favorite experiments. It was done by former student of this previous author. In this experiment, the gas was segregated into two spin fractions, coded in color. This is a series of photographs of the gas in the cylindrical, in the cigar-shaped trap. In half of the trap, the atoms were in spin 1 state, in spin up state, designated by red color. In the other half of the trap, the atoms were in the opposite spin state, and there was barrier in between. Then the barrier was was suddenly removed, and the two gases started colliding, started to flow towards each other. Separately, these are two ideal non-interacting Fermi gases, very simple systems, and they started flowing towards each other, and they were unable to penetrate into each other, because each atom was non-interacting with the same spin state atoms, but with the other spin state, for the other spin state there was strong scattering cross section. The two parts of the cloud started moving towards each other, hit each other, then even bounced back. This graph is showing trajectories of the center of masses of the two halves, trajectories of the center of masses versus time. There was some mixing, but it was ridiculously slow. So depending whether the Fermi two spin states mixed or not, very different properties. Okay, now let's look. It's time to look at misconceptions again. So far, we've been looking, this is again very important diagram, scattering length versus magnetic field. So far, we looked at this right side, where the scattering length is negative. Now let's look at this region where the scattering length is positive. And now our point is attracted to this branch. Scattering length goes high. And let's look back into the year 1933. 1933, Stoner formulated the concept of ferromagnetism. Edmund Stoner pointed out that, look, to get ferromagnetism, we don't need any lattice like in the metals. It's enough just to have some repulsion between different spin states. Let's try to translate Stoner's idea into ultra-cold gases. These are two here on the left and on the right. There are two pictures. This is normal state. Again, we are considering ultra-cold atoms, mixture of two spin states, very similar to electronic gas, like in electronic gas. Electrons with spin up and spin down. Here are neutral atoms in two orthogonal internal states. So this is a normal phase where all spins are mixed. This is ferromagnetic phase, where the two spin states are segregated. This is on one side, this is, let's say, spin up state, on the other side, spin down state. How to achieve this naturally? In that previous non-penetration experiment, two spins were separated purposely. How to make the gas to separate into two domains by itself, naturally? let's compare energies of these two states. Normal energy of the normal phase. This is the Fermi energy, plus the mean field repulsion. Here A is positive. So all spin states are mixed. It means they interact with each other and there is repulsion. On the other side, the energy of the two separated states. It's a ferromagnetic state. The atoms are separated into two domains, which means they do not interact, just interaction along the border, which we omit for simplicity. We are just looking at qualitative effect. But the Fermi energy is higher because each gas is occupying twice smaller volume, which means the density has to be a factor of 2 larger. And for large enough A, ferromagnetic phase should win. Ferromagnetic phase should have lower energy, which means the gases should separate. That's the idea. Now let's move to the physics. That's the simple model, but let's move to what this model was missing. What this model was missing, and why this ferromagnetism is not a part of the physical reality, at least for the gases with S-wave interactions. Here, for the effect, we need positive scattering length. What does it mean in the language of two-body interactions and two-body potentials? Okay, the graph I have drawn already at least twice. R, distance between two atoms. V of R, interaction potentials. Positive scattering length means that there is a bound state. Bound state not very far from 0. And the bigger the scattering length, the closer this bound state is, the higher this bound state is. Approximately, energy of the bound state is minus h bar squared 2m a squared. The size of the bound state in centimeters grows up, which means wave function of this bound state becomes more and more overlapping with the unbound wave function of two atoms. And this is a way to for three-body collisions. If there are two atoms, they cannot get into the bound state. They have no way they get rid of extra energy. But if the third atom comes in, it can collide with these two and take extra energy away. And these two atoms, they get into the bound state. So, and before A becomes big enough, this three-body binding process becomes so strong that it makes the system non-equilibrium. Just the system heats itself from this chemical reaction. And so Stoner ferromagnetism, unfortunately, for this reason, does not exist, at least for systems with S-wave scattering. In the beginning of yesterday's lecture, there was a question: why there is about 1 micron distance between the atoms? Why not to put the atoms closer? Yes, you can put them closer, but if you start putting them closer and closer, there is a much bigger probability of such a three-body collision and the chemical reaction. So these three-body effects prevent the gas from becoming denser. You can make interparticle distance smaller by order of magnitude, 100 nanometers, but if you put them even closer, this three-body process heats up the gas immediately. It goes much faster than any thermalization. So dense ultra-cold gases can exist only as a non-equilibrium species, like when you even cannot define temperature. So they can live only for a split second, depending on the high density which you choose as a target. And as for the misconceptions, this ferromagnetism, it was discussed seriously a few years ago. The authors of a previous beautiful experiment even reported evidence for Stoner's ferromagnetism, but later they have shown experimental proof that this ferromagnetism was non-existent. Though, despite initially wrong experiment, they ignited very interesting discussion, which helped to understand the role of three-body interaction, which in this ferromagnetism. So initially, it was analyzed in the frame of theory involving two-body interactions, and after some discussion, it was found that the theory was incomplete. So wrong ideas can be very fruitful. They help in deep understanding. Again, we shall go across the Feshbach resonance. But first, we shall look at the idea from 1968. Still, we are considering fermions with around Feshbach resonance, which allows to vary the interactions. Let's look at the paper of Keldysh and Kozlov, 1968. They were considering excitons, but that's a minor detail, unimportant for us. They posted a question. Let's look. And we shall not go from the left to the right, we shall go from the right to the left. Suppose there are pairs of fermions. And the way the pairs appeared doesn't really matter. It could be Cooper pairs, or it could be just excitons. Exciton, it's a bound state of an electron and a hole. And the size of these bound pairs for exciton can be huge. The size of the exciton can be larger than the interparticle distance in the semiconductor. And let's slowly increase I'm simply translating the paper of Keldysh and Kozlov. And let's slowly, gradually increase the interaction inside each pair. The exciton shrinks smaller, 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 and smaller, like I'm showing on this graph. Here in the middle, the excitons are about the size of the interparticle spacing. And then the excitons become even smaller. They become each exciton becomes a point-like particle, so that the internal structure is even unimportant. And they posed a question: is it possible to do such a smooth transformation? And it occurred. And here you can see. Notice the date. Question posted in 1968. The answer to this question was already contained in Bogolyubov's version of the theory of superconductivity in 1958, 10 years ago.
Before.
Yeah, yes, thank you. 10 years before this question was, the humanity had a tool to answer this question, just it was not recognized that the answer was contained in this theory. Even Bogolyubov did not recognize that. That's actually a signature of a really strong theory. write theories which are deeper than you really understand them. So such transformation was already contained in Bogolyubov's theory. The theory was not quantitative, but qualitatively it occurred to be absolutely fine. So this is the Hamiltonian. And Bogolyubov was, of course, considering the Cooper pairs. That this is the Fermi sphere. And again, the subject, the object of this theory are fermions in two spin states, electrons, or it could be atoms. Even maybe Bogolyubov didn't think about that. There was and the fermions in opposite spin states, they can scatter only into other states on this Fermi sphere, and they pair. So Bogolyubov's pairing was shown before that by Cooper, and Bogolyubov has found the solution in the form of a direct product of Cooper pairs. So in Bogolyubov's theory, all fermions are paired, and the momentum of the pair of all pairs is 0. And there is a parameter of this theory, G. It translates up to renormalization or cutoff parameter, which we discussed with Vasily yesterday. I think you asked the last question of yesterday's session. So all interaction up to the cutoff parameter or renormalization is in this constant G. And this constant G is the scattering length. And you know, the scattering length can be varied by tuning the depth of the potential or by the Feshbach resonance, which we know now. So Bogolyubov's theory was considering only situation where this interaction potential is not deep enough, so that there is no bound state. There is no bound state. It would have appeared if the potential were deeper. But
So you are considering here as a kind of reduced Hamiltonian where pairing occurs only between P and minus P.
Yes, I
by hand insert this in the Hamiltonian.
Yes, already simplified to zero central momentum of the particles.
And for such a Hamiltonian, indeed, mean field solution is exactly the thermodynamical limit. But if you include pairing between electrons with the total momenta not equal to 0, then you have fluctuations, and it is very tricky to take them into account. This works on BCS side, more or less.
I agree. I fully agree, and I will show my agreement maybe in 2 slides from now. Yeah, thank you for this comment and for pointing out this simplification that already in this Hamiltonian all pairs already have 0 momentum. So in this initially in the theory G was negative, but formally this solution is a product of Cooper pairs. It remains a solution even for positive G and positive scattering length. And it means it's possible to expand this solution to the situation where there is bound state for the fermions. Why? A comment: why it is tricky to, why it is even worth of discussing a question of taking a system of fermions and slowly converting them to the ground state of bosonic system. Look, this is fermion system and this is bosonic system, because each pair of fermions, it's a boson, it's a point-like boson. So we even know the solution for the left side. It's a Bose-Einstein condensate. So here, a gas of switching to the language of superconductivity, a gas of Cooper pairs should smoothly transform to the gas of Bose-Einstein to the gas of bosons, to the Bose-Einstein condensate. Why is it tricky to take two fermions and make a gas of bosons from them? Why a many-body system is needed? On one hand, it's very simple. You consider two fermions which have a bound state, and you just bind them. Just make a molecule, and that's a boson. However, for binding, you notice a third particle is needed, which removes extra energy, and it's a chemical reaction with energy coming out. So it is not possible to keep the system at low temperatures. It's not possible to keep the system degenerate. The question is how to do everything remaining in the ground state of a system. So it's not the way to go. The way to go is to take a interaction potential between two fermions which is not deep enough, and slowly decrease the depth. And this would convert a gas of large Cooper pairs to smaller Cooper pairs, and then to a Bose-Einstein condensate. Let's do that in the language of Feshbach resonances, because for atoms, it's not possible to change the depth of interaction potential. It's electrostatic forces which are very hard to manipulate. But fortunately, there are two scattering channels which correspond to different spin orientation, to different electronic spins of two interacting atoms. Two valence electrons of two interacting atoms can be either in spin triplet state, parallel spins, or spin singlet state. And spin triplet state, it has huge magnetic moment, and it is susceptible to magnetic field. So let's consider first let's consider small negative scattering length, where in this side of the graph, at large magnetic field, it means the triplet potential is much below the singlet potential, because this gap at a large distance, this gap is a magnetic field times Bohr magneton. This gap is large. And the atoms are primarily in this electronic spin triplet state. This is the energy of two atoms. Then we slowly decrease magnetic field and sweep through this bound state. And this mixes a singlet bound state to the state of two atoms, and the atoms become bound. And this way, and this situation corresponds to being in this region of the Feshbach resonance. So we swept across this dangerous region of positive large scattering length, and nothing tragic happened, unlike an attempt to obtain Stoner magnetism, because we didn't go through from the left to the right. We went from the right to the left, from already small binding between inside Cooper pairs. And this binding needs Fermi seeds. It's intrinsically a collective effect. So that's what I told you. It's the so-called Bardeen-Cooper-Schrieffer to Bose-Einstein condensate crossover. So on this side of the graph, the gas of atoms is supposedly described by the Bardeen-Cooper-Schrieffer theory. And then it is transferred, it is gradually, adiabatically, and reducibly transferred to Bose-Einstein condensate of molecules lithium-2. from two fermions, it's possible to make bosons, and this Bose gas condenses. That's the idea, and I'd like to report an experiment on that. Experiment, well, first there is interest in a model, and second, in quantum mechanics, it's always something is needed to see the actual phenomenon. Also, this experiment is done with a two-dimensional gas. What this graph means and what is measured. What would be the signature, observable signature of this crossover from Fermi system to Bose system? Fermions, we used that already. Fermions have Fermi pressure. In an experiment, pressure was measured inside this disk-shaped cloud in the middle. And as the system becomes more bosonic, the pressure should go down, because bosons have no pressure, at least when they are not interacting. As I told you yesterday, it's impossible to get a completely non-interacting Bose condensate of completely non-interacting bosons. But at least as those point-like particles become less and less interacting, the pressure should go down. So in experiment, pressure was measured inside a cloud of atom, and imagine simplest way of measuring pressure, it's applying force to something and dividing this force by the area, so pressing on something by a piston. And this is a system we are not allowed even to touch, because it would heat with any device would have heated this system. How pressure was measured in the middle. Oh, by the way, this is connection to this graph is connection to your question about precision of that simplified version of Bogolyubov's theory. Look, this here on this graph, I plot pressure versus the interaction parameter. The right-hand side is the Fermi gas of atoms. The left-hand side is Bose gas of molecules, and the blue curve is that simplified Bogolyubov's theory, and the lower curve, it is the more precise calculation including fluctuations of the order parameter. And indeed, Bogolyubov's theory quantitatively is doing very well only in the Bardeen-Cooper-Schrieffer limit of small interaction, but as the system becomes more bosonic, the simplified Bogolyubov's theory, yes, indeed, it is off in the amount of interactions. It is off by a factor of 3. Okay, so this was for three-dimensional system, and you can notice the measurement was about flat system where the motion is two-dimensional. And the trick about two-dimensional system was that for two-dimensional system, the simple mean field Bogolyubov's approach was completely off. It gave qualitatively incorrect result. This is prediction for two-dimensional system. So this made the experiment more valuable. How to measure pressure inside. This is how a series of two-dimensional systems was created. For each gas, there was a separate disk-shaped trap. It was created by a standing wave, and each antinode was a maximum of intensity. Each antinode was a trap. Each antinode was a trap, and a series of such cloud was photographed from a side. So each stripe is a separate cloud, and even the center of the cloud was not seen, but the pressure had to be measured in the center of the cloud. How to anyway to perform such a measurement? Well, one can integrate this photograph along this direction and get one-dimensional profile of the density. But the system is two-dimensional. How to get, and it's spherical, it's cylindrically symmetric. It's a disk. To get two-dimensional density distribution, there is a constraint of this system, cylindrical symmetry, which means it is possible to do inverse Abel transformation. And from this integral of density n1 of x, it's possible to recover the whole cylindrical density. So the cylindrical density was recovered. One can find density everywhere, including the center. And after that, there is a force balance equation. There is a force balance equation that gradient of the pressure is balanced by the gradient of the trapping potential times the density. And by integrating this equation, it is possible to find pressure at any point, including the center. So indeed, this crossover from the Fermi gas to a gas of bosons was observed. Okay, so this was many-body physics with strongly interacting fermions. And from fermions, it is possible to produce bosons and to do boson physics. And now I'd like to turn back to the question of preparation of ultra-cold gases and cooling ultra-cold gases. So the question about today's current research. I was telling you about some phenomena. For those phenomena, the gas is cooled and trapped. And let's ask a question. What's about the number of atoms? And is the number of atoms sufficient for doing physics? These are examples. In the magneto-optical trap, it's up to 10 billion atoms in principle, but they're hot. So it's almost no many-body physics with such atoms. We need degenerate atoms. In the first BEC, there was 10,000 bosons. In the biggest BEC, 100 million bosons. With the fermions, just 1 million. I like fermions because from fermions you can do Fermi physics, and you can glue two fermions into a boson and observe boson condensation. Whether this number is enough? Well, some interesting experiments were done. From this perspective, this number is perfectly enough. By the way, the record low temperature, it was achieved 0.45 nanokelvin. It included only 2,500 boson atoms. So now let's look at an example where such number of atoms is insufficient, and this something which could motivate to developing methods of laser cooling and trapping. And of course, to significantly increase the number of atoms, some deep scientific ideas are needed. Let's look. Again, our clock goes back to the 60s. Let's look at the phenomena for which those number of atoms are insufficient. 1967, Anderson put up the following idea. He considered an ideal Fermi gas. Making ideal Fermi gas, non-interacting Fermi gas of atoms is easier. Just polarize them into a single internal state, a single spin state. And there are no S-wave interactions between alike atoms. And then let's introduce just one impurity, something those atoms would interact with, this red dot. Introduce this impurity. And Anderson points out that introduction of such impurity makes the state of the system, of the Fermi gas completely orthogonal to the initial state, but only in the limit of infinite number of fermions. A very interesting phenomenon. You introduced seemingly small perturbation, just one particle, and you make the state completely orthogonal. It means some small process which cannot be done adiabatically. So one impurity makes wave function orthogonal, but let's look how this overlap integral behaves with the increasing number of atoms. I hope you would appreciate this integral behaves as the number of atoms to minus this number. What's sine squared delta? Sine squared delta is the phase shift in scattering. For simplicity, Anderson was considering only S-wave scattering. Of course, it's phase shift, so sine can be put 1. And nevertheless, the overlap integral goes approximately as n to the power minus 30. Oh, by the way, let me remind you what the phase shift is, or connected to the scattering length A, which we used before. Okay, I have a graph, but it's already busy. I will redraw it. Remember, the S-wave scattering changes only the 0th harmonic in the Bessel expansion of the wave function. So this is the Bessel function. And all interaction can only add phase shift to here. Small repulsion means the phase shift is smaller, and just this Bessel function shifts a little bit. And strong means shift means the shift is by pi over 2. That's the strongest possible interaction. And so strongest possible interaction, delta naught equals pi over 2, or A scattering length equals infinity. In fact, scattering length is connected to the phase shift like this. It's minus 1 over k tangent delta naught.
I don't remember. Is this fancy formula from the original paper of Anderson? Or
Yes, yeah? yes. I looked up that paper yesterday. I was not sure. I looked up again. Well, this formula is from Anderson's 1967 paper. And then, as you see from this formula, A, as it goes from minus infinity to plus infinity, nothing special happens. Just phase, scattering phase changes a little bit. So this is how the overlap integral goes down, and let's plug in the numbers. So for current situation, for Fermi gas, for current Fermi gases, 1 million atoms. This overlap integral is even more than a half. It's 0.6. And if we load the whole magneto-optical trap into some device which would make 10 billion atoms degenerate, then overlap integral goes down, and only in this situation it becomes less than a half. And Avogadro number brings slightly more than 10% overlap. So there is a phenomenon which is clearly very hard to observe with the current number of atoms, and probably it would be masked by another phenomenon like appearance of a polaron.
But you see, even if this is an Avogadro number, This is just 0.1.
Which is, of course, much better than 0.63. And the appearance of a polaron strongly distorts a system. So these are the two effects which could be competing against each other. And so it's maybe in demonstration of each effect, maybe it's not necessary to show infinite signal-to-noise ratio. It's important to show existence of that this effect you are searching for is stronger than competing explanations. So maybe some Markov with billion atoms already could be enough to distinguish orthogonality catastrophe from other phenomena, but that's a qualitative question. But of course, I hope this is enough as a motivation to search for improving number of atoms. Okay, what's about current temperatures? I told you that record temperature is half a nanokelvin, and this is temperature in nanokelvin for us as for physicists. Relative numbers are important. So important temperature unit is the Fermi energy, and both Fermi energy is important energy scale both for fermionic systems and for bosonic systems. For bosonic systems, Fermi energy is also meaningful. For example, temperature of Bose-Einstein condensation. Temperature of Bose-Einstein condensation. It's 0.2 of the Fermi energy. One can also write definition of the Fermi energy. It's independent of whether it is a gas of bosons or fermions. It's h bar squared over 2 mass of boson over 2 times the expression involving the density. From 2 fermions, you can always make a boson. So Fermi energy is meaningful and important unit for us is temperature in the units of the Fermi energy. What's the current temperature in today's experiment? The lowest temperature, when the temperature is still meaningful, it's the energy gap between the one particle energy levels, which in case of parabolic trap, it's h bar omega. So the lowest temperature, which in principle can be achieved, it scales as 1 over the number of atoms to 1/3. In parabolic trap, the Fermi energy is number of atoms to 1/3. So to speak about today's for fermions, maximum n is 1 million, which means smallest temperature is 1% of the Fermi energy. Of course, you can think of you can immediately think of phenomena which are below 1% of the Fermi energy. For example, conventional superconductivity. If it is 2 Kelvin compared to 1,000 Kelvin, compared to 10,000 Kelvin, that's an accessible scale for the atoms. So there is again, for getting lower temperatures in units of T over EF, there is a demand. There is a demand to increase the number of atoms. How this can be achieved? And now I'm talking about current research. Our time machine is now in today's days. As you heard before, one may cool to degeneracy in the focus of a laser beam. If we start with magneto-optical trap, this is the cloud, the wrongfully whitish cloud. There is 1 billion of atoms. The focus of a laser is small. The focus of a laser is small. Not all atoms are intercepted, and also a number of order of magnitude of atoms is lost during evaporative cooling. Plus, let's think again about nanokelvin. I was persuading you that T over EF is meaningful, but let's talk about nanokelvin. Nanokelvin is also important because let's suppose you can cool some species to huge nanokelvins. Then you can use your species as a refrigerator for another sort of atom. So nanokelvins is also important. How to get absolute nanokelvins. How to get absolute nanokelvins. Now I will be criticizing this very nice dipole trap created in focus of a laser beam. You know, very simple way of cooling. It's expansion. There's nothing easier. You expand the gas, it cools. In optical dipole trap, you can also expand. That's very easy. You lower just the power of your laser. The height of this potential goes down, and the potential opens up. Which means the gas inside becomes wider. However, I assume you learned undergraduate quantum mechanics very well. You know that in this Gauss-shaped dipole trap, the number of energy levels is finite. As you get your trap lower, the number of atoms, the number of energy levels becomes smaller and smaller. Not enough energy levels. No way to hold no way to hold the fermions inside. And similar story about bosons. Because of interactions, they don't sit on the same energy levels. So with this nice tool, optical dipole trap in the focus of a laser beam, you cannot do a very simple strategy of cooling. You cannot do just expansion. Some expansion can be done, but there is a limit for that. Let's overcome this limit, and let's overcome the limit in the number of atoms. The way to overcome this limit is slightly change the principle of trapping. Before I told you about trapping in focus of a laser beam. It's maximum of laser intensity. It's so the laser frequency is much below the transition frequency in the atom, and the atoms are trapped inside the laser beam. Let's change the situation. Let's move the laser frequency up. Let's move the frequency up so that it is higher than the transition frequency. Then the atoms are repelled from illuminated region. Is anybody here connected to plasma physics? In plasma physics, there was a great idea about holding plasma. Plasma is repelled from radio frequency field, and this is a way to create walls for trapping plasma. This is an idea, I think, from the 50s. Here the same can be done, and actually is being done. So in such for such laser frequency, the gas can be trapped between almost rigid walls created by the lasers. How this trap can work? Well, it's easy to create two walls. It's just two sheets of light. And what's about, and then the remaining other walls can be created by a cylinder. A cylinder of light would be a trap. In fact, the trap which I'm showing to you, it's already existing, but those traps which were built before, they are small, and the real goal the interesting goal is to make such trap big. And if such trap big, it can swallow the whole magneto-optical trap, the whole billion or 10 billion atoms. And this is what my colleagues are currently working on. What can be achieved in such trap with flat potential inside and with big number of atoms. Now I'm switching to future research. And I'm really interested if you say that the ideas I'm translating is some interesting misconception and suggest something interesting. And the field which can be achieved with such a large flat trap is imbalanced Fermi gases. So far, I've been telling you about a mixture of fermions in two spin states with equal populations. So there is one-to-one matching between fermions in spin up and spin down states. Let's consider the situation with unequal densities. And again, we can look at great ideas back from the 60s. Such gas was considered in the 60s by Fulda-Ferrell and almost immediately after by Larkin and Ovchinnikov. For fermions, size of Fermi spheres depend on the density. Because Fermi momentum is square root of the Fermi energy, and Fermi energy is 2/3 power of the density. Let's suppose there is a majority species, let's say spin up. This is that red Fermi spheres which extends from 0 to the border of the red, and there is minority with there is minority which is designated as blue. And for Cooper pairing is impossible in this situation, at least for S-wave interactions. Cooper pairing is impossible because two Fermi spheres are so much mismatched. But it is possible it is still possible to pair for the atoms. Who would pair? In the dark, well, is it visible? Okay, it looks hard. This region is slightly darker. So particles from this slightly darker red region would pair with those from the darker blue region. And if we add up together momentum of red particles and blue particles, you would see it's finite. So unlike the Bardeen-Cooper-Schrieffer theory, it would be pairing pairing into a state with a finite momentum, and even more interesting, condensation of pairs into a state with a finite momentum. So this is one phenomenon which could be accessed with imbalanced Fermi gases. In fact, there were already attempts to study imbalanced Fermi gases, but in harmonic traps. In harmonic traps, the situation was very plain. It was always a paired core appeared, a simple balanced gas with the same number of atoms in spin up and spin down states, and just polarized gas in one spin state in the edges. You can see data from experiment. This axis is density, and this is coordinate. And you can see this black curve. It's the density of it's the difference between the density of the two species. So in the center, all is paired, and in the wings, the majority atoms are pushed up. Pretty simple situation. So Larkin, Fulda-Ferrell and Larkin Ovchinnikov superfluidity still not achieved.
But why do you think that when you create these hard walls, you can avoid phase separation? You can have phase separation in the longitudinal direction, so on the up part of your cylinder you have more or less spin balanced gas, and down part you can have spin up only. Phase separation can go with different ways in principle, right?
In this, well, Well, in this cylindrical trap, all the potential inside is flat, which means there is no preferred direction. It might be phase separation, but it would be in some randomized domain. Well, since it's unexplored area, I don't have an answer whether phase separation would still happen or not. But if there is some randomized phase separation, still it would be some interesting result. Of course, not as interesting as the Larkin and Ovchinnikov and full differential superfluidity. And by the way, in such trap, nothing prevents us from changing the size of the trap. The walls can be put closer to make high density gas to get a fast evaporation. And evaporation with losing just a small number of atoms. Or after the gas is degenerate, the walls can be spread out to basically any unlimited value, and this is a way to achieve low temperatures just by the cheapest way, just by expansion. Expansion is the easiest way of cooling. It would be same temperature in the Fermi energy units when you expand the walls. But it could be smaller value in nanokelvin, and which means this gas can be used as a coolant for another gas. So such cylindrical trap, it's a way to forget. Yes, please.
Can I ask a question? So it's a cylindrical trap. It's only one-dimensional.
It's three-dimensional, because. Look at these two walls. These two walls, those are just sheets of light. You take a Gaussian laser beam, make it go through a cylindrical lens, and make it flat. This is one flat beam, one more flat beam. This cylinder, it's shallow. This cylinder, it's empty inside. It's just this. Well, I'm sorry, it's not cylinder. It's a tube. It's a tube with very very thin walls of light. So it's fully three-dimensional trap.
So and this trap is tuned in the blue shape.
Yes, exactly. The frequency is higher than the frequency of an atom. Of a transition frequency in an atom. So such trap, it's first, it's since it can be expanded, it's a way of getting unlimited low temperature in nanokelvin, and also since it is possible to intercept absolutely all particles from big magneto-optical trap, it's a way of getting large number of atoms and meaning low temperature in energy units.